A clay tablet scratched more than 2,000 years ago can tell us that our planet is rotating differently today. Not because the scribe measured milliseconds. He did something much simpler. He wrote down an eclipse. A total solar eclipse is brutally sensitive to timing. The moon's dark central shadow, the umbra, sweeps across only a narrow strip of Earth. Move Earth's rotation by a little, and that strip shifts east or west. Over a few minutes, the difference is small. Over centuries, tiny changes in the length of a day accumulate. By the time you calculate an eclipse from ancient Babylon or China, the predicted shadow can end up far from the place where somebody wrote, in effect, "The sun disappeared here." That is the trick. Astronomers can calculate where the sun and moon should have been using the laws of orbital motion. They can run those calculations backward for centuries. Then they compare the calculated eclipse with historical observations. Was it total? Was it partial? Was it seen before sunset? Which city reported darkness? A record that sounds like a piece of history becomes a measurement of Earth's rotation. The useful quantity is called delta T, written delta T. It is basically the difference between a uniform astronomical time scale and time based on the actual rotation of Earth. Modern clocks are wonderfully steady. Earth is not. If delta T for an ancient date is wrong, the moon may still cross the sun at roughly the right moment in its orbit, but Earth will have turned to the wrong angle underneath the shadow. Take a city in the ancient Near East. An eclipse calculation says Totality should have passed hundreds of kilometers away if Earth had rotated at one assumed rate. A surviving observation says the sun was completely covered in that city. You now have a constraint. Earth must have been rotated to a slightly different longitude at that moment. One old sentence can eliminate a whole range of possible rotation histories. The best historical material is not one perfect record. It is lots of imperfect records. Babylonian astronomers kept eclipse observations on clay tablets. Chinese court astronomers recorded eclipses in chronicles. Medieval observers in the Middle East and Europe left reports too. Some are precise. Some are annoyingly vague. A phrase like, "stars became visible," is useful because it may suggest a deep eclipse. "The sun was eaten" is memorable, but scientifically it needs context. And yes, this gets messy fast. Ancient calendars have to be converted. Place names change. A copy made centuries later may contain an error. Clouds can turn a total eclipse into no observation at all. Researchers do not treat every dramatic sentence as a stopwatch. They compare many records, rate their reliability, and look for a history of Earth's spin that makes the whole collection fit. A major modern analysis by F. Richard Stevenson, Leslie Morrison, and Catherine Hohenkirk combined ancient and medieval eclipse records from 720 BCE to 1600 CE with later observations, including lunar occultations, extending the reconstruction to 2015. Their results showed that the mean solar day has lengthened on average by about 1.8 milliseconds per century over that long interval. 1.8 milliseconds sounds ridiculous. A blink is vastly longer. Your phone would never notice it during lunch. But the effect compounds. Earth makes more than 365 rotations every year. Give a tiny timing error centuries to pile up, and the accumulated difference becomes large enough to move an eclipse track by enormous distances. That sounds small, but it matters. Why is Earth slowing at all? Mostly because of tides. The moon's gravity raises tidal bulges in Earth's oceans and also deforms the solid Earth. Because Earth rotates faster than the moon orbits, the tidal bulge is carried slightly ahead of the Earth-Moon line. The moon pulls back on that bulge. Earth loses rotational angular momentum, while the moon gains orbital angular momentum and gradually moves outward. Apollo astronauts left laser reflectors on the moon, and lunar laser ranging shows that the moon is still receding from Earth by roughly 3.8 centimeters per year. The same Earth-Moon interaction that moves the moon outward is slowly breaking Earth's rotation. On very long timescales, the day gets longer. There is a complication, though. A simple tidal model predicts a long-term increase in the length of day, closer to about 2.3 milliseconds per century, larger than the roughly 1.8 milliseconds inferred from historical observations. Earth is not a rigid spinning ball with one break attached to it. Ice matters. So do the mantle, the liquid outer core, the oceans, and the atmosphere. Since the last ice age, land that was crushed under enormous ice sheets has been slowly rebounding. Mass is being redistributed. Movements inside Earth can exchange angular momentum between the mantle and core. Winds and ocean currents can make the rotation slightly faster or slower over shorter periods. The long-term tidal braking is there, but other processes ride on top of it. You can see the same principle with a spinning office chair. Pull your arms inward and you spin faster. Stretch them outward and you slow down. Earth's mass shifts are vastly more complicated, obviously, but angular momentum still has to balance. A few milliseconds in the length of day can contain information about the moon, the oceans, melting ice, the mantle, and the core. The eclipse itself is a ridiculous piece of geometry. The sun is about 400 times wider than the moon, but it is also about 400 times farther away, so the two appear almost the same size in our sky. That coincidence lets the moon cover the bright solar disk, while leaving the sun's outer atmosphere, the corona, visible around it. Just before totality, the edge of the sun often breaks into tiny points of light. These are Baily's beads. The moon may look like a smooth circle from your backyard, but its edge is covered with mountains and valleys. Sunlight passes through the low valleys, while higher lunar terrain blocks the rest. For a few seconds, the landscape of the moon is projected in light from nearly 400,000 kilometers away. Then the beads collapse toward one last, brilliant point. With the faint corona appearing around the black moon, it creates the diamond ring effect. Once direct sunlight is completely gone during totality, the corona can be seen with the naked eye. Outside totality, proper solar eye protection is still required. Regular sunglasses are not enough. The corona is normally lost in the glare of the solar surface. During totality, the moon becomes a natural occulting disk and blocks that glare. Long before spacecraft could make artificial eclipses with instruments called coronagraphs, total eclipses gave astronomers rare access to the sun's outer atmosphere. They still remain useful because the very inner corona can be difficult to observe from space-based coronagraphs in exactly the same way. Eclipses also repeat in families. After about 18 years, 11 days, and 8 hours, the sun, Earth, and moon return to nearly the same geometry. This is the Saros cycle. The extra 8 hours matter. Earth rotates about a third of a turn during that time, so the next eclipse in the same Saros series occurs roughly 120 degrees farther west in longitude. Same cosmic arrangement, different part of the planet gets the show. A total eclipse can last only seconds at one location, or several minutes under favorable geometry. The path of totality is narrow because you have to stand inside the moon's umbra. A person a modest drive away may see a bright crescent sun while you are standing under a black disk and a white corona. Near total is visually impressive, but it is not the same physical experience as totality. And during those few minutes, Earth itself reacts. The light level collapses, air temperature can drop, bright planets or stars may appear, shadow bands can ripple over pale surfaces just before and after totality, produced when atmospheric turbulence distorts the last thin sliver of sunlight. Birds and insects sometimes change their behavior as the environment abruptly resembles dusk. Not every species responds, and not every eclipse produces the same effect. There is another nice twist in the timing story. We can predict modern eclipses extremely well because we know the current positions and motions of Earth and the Moon with high precision. But go far enough into the past, and Earth's irregular rotation becomes one of the main uncertainties. So historical eclipses are both something we calculate and something that corrects our calculations. That feedback loop is why an ancient observer matters. Someone stood under a darkened sun, wrote a line on clay, bone, paper, or parchment, and preserved a location in time. Centuries later, orbital mechanics tells us where the moon's shadow should have gone. The mismatch tells us how Earth was turning. A solar eclipse looks like the moon briefly switching off the sun. Scientifically, it is closer to a moving ruler laid across a rotating planet. The shadow marks where Earth was pointing at a particular instant, and ancient humans accidentally left us thousands of years of calibration marks. So the next time the sky goes dark in the middle of the day, there is more happening than a spectacular alignment. The corona is appearing. Lunar mountains are carving beads of sunlight. The Saros clock is continuing an 18-year rhythm, and buried inside the exact path of the moon's shadow is evidence that even the length of a day is not fixed. Earth keeps time, but it is a clock whose rate slowly changes, and eclipses let us read the error.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!